Hello everyone, welcome back to ECE350. Today I'm going to talk about wave polarization, linear polarization, and circular polarization. This is lecture 20 of chapter 7. Okay, before I talk about polarization, let's see how wave propagates through the medium. If you see the first one over here, your wave going up and down, all right, one propagating into or the y direction. Actually, this is propagating the y direction here. So it's going up and down in a kind of sinusoidal wave, right? On the second one over here, it's not in one direction, it's all over. Can you see that? It goes almost around that y axis. When it's propagating, it's going around the y axis. So if you look at the this figure and this figure over here, it shows a little bit clearly that how this one propagating is going up and down in a sinusoidal fashion, and this one actually is circulating around the axis of propagation. This one is circulating around the axis of propagation. All right. So how if you look at the tip, of the vector, for example, you look at the E over here, and also this one E over here. If you look at the tip of the vector right here, this is the tip of the vector, right? This is the tip of the vector of the propagating signal. How the tip of the vector going propagating in the media, if we trace that tip of the vector or locus of the vector, that is called polarization. Okay, so you can see that first one is going up and down, and this one is circulating around the axis of polarization, axis of propagation. Okay, so now come over here. Even if you can see better over here, so now if you put a plane that is perpendicular to the axis of polarization, for this one here, this is the axis of propagation, right? That's why your wave is propagating, and this is the plane, xy plane is perpendicular to that axis of propagation. Now if you have that plane fixed at say this plane is fixed at x equals 0. Now if you look at the tip of the vector, how that vector look like when you observe from that plane, in this case xy plane, which is perpendicular to the direction of propagation, you will see that for this one here, your tip of the vector goes highest over here, then it's coming down, right, and it becomes 0 over here and goes this way, and highest here, and it's just following this line. Can you see that? So that is let me take a different color here. So that is the line, the tip of the vector following back and forth all the time, right? So that is line over here. So z is the axis of propagation, and your tip of the vector that propagating in the z direction is following this up and down line over here, right? So this is called linear because it's following a linear path. The tip of the vector is following a linear path on the y-axis, on the xy plane when it's propagating to the z direction. Okay. Come over here. The second one over here. Now you have the same xy plane over here, right? If you look at the xy plane and follow the tip of the vector, you'll see that vector will make a circle on the xy plane. So xy plane again is at z equal to 0, right? And you're looking at from that plane, you're looking at the tip of the vector propagating through the z direction. And if you look at the tip of the vector, it will produce a circle right here. So it's called circular polarization. Okay, so polarization is you're observing the tip from a plane that is perpendicular to the direction of propagation. And if you look at this one here, and if you do the same xy plane at z equal to 0 here, so your planes are moving, then you're looking at the tip of the vector of the signal propagating in the z direction. If you follow the tip, you will see there's the elliptical you get an elliptical propagation on the xy plane. So there are three propagation polarization here: linear over here, circular over here, and elliptical over here. Today we're gonna talk about linear and circular, and tomorrow we're gonna talk about our next class. We're talking about elliptical one. So now let's get back to our let's do only electrical signal over here. So what I'm saying is the polarization of a uniform plane wave describe the locus traced by the tip of the E. We're talking about the only electrical signal here. E vector in the plane orthogonal to the direction of propagation. That's why the xy plane. If a signal going to z direction, xy plane is the orthogonal to the direction of propagation at a given point in space as a function of time. So if you're fixing the plane and you're looking at the tip of the signal, how it's going, how is seen from the plane of perpendicular to the propagation, that is the polarization. So now we have an electrical signal over here. It's an x component and y component, right? Then both in positive z direction. So this one will be here ex0, it will be negative jkx, and this is the ey0, it will be j kx, and these are the magnitude over here. These are the magnitude over here, right? So now both of them over here, both of them complex, because they have both real and imaginary part. So if we say that ex0 is ax and ey0 is ay ej delta, that means delta is the phase shift between x component and y component. So delta is the phase shift between x component and y component. So then then in the time domain signal, your ECT come with this over here, right? So now look at that. You know how to go from phasor domain to time domain, right? How to go from phasor domain to time domain. So omega t is introduced into the time domain, all right? So it's a time domain signal. Now, again, I wrote this back here because I want to use it. So time domain signal back here again. So now if you look at here, this is the time domain signal here, right? I just wrote it back here too. Now, to make sure that I can go from here to here, right? So now if I try to get the magnitude of the signal, so that x part squared plus y part squared and square root, right? So that is right here, okay? And if I try to get the inclination angle, that means if this vector, how much angle is making to reference axis, that is over here. So that would be the y component over x component, right? Tangent tan inverse y component over x component. All right, so now let's move forward here. So now now do some special case over here. Let's say that my signal, let's go back here, or this one here, my signal over here, it could be in phase when delta is 0, right? So delta is 0, that means both x and y are in phase. If delta is pi, which is 180, is completely out of phase, right? So if I do that over here, so delta equal to 0, I put delta equal to 0, that signal right here, right? Delta equal to 0, so both are in phase, right? So that means cosine omega t minus kg can be out as a common factor, then you have x component and y component. But if it's pi, which is here 180 out of phase, if you do that, look at here, is sine, this sign becomes negative here because of your trigonometric function. So that is right here. So this is two, one is in phase, one is out of phase. Delta equal to 0, they both are in phase. And what this means, delta equal to 0 over here, so if the x component and y component is right on it, right? And delta equal to pi means x component this way, y component could be other way. So this is your x component over here, this is your y component here. So x component, y component could be in phase, delta equal to 0, and this is delta equal to pi. So there's a negative sign introduced over here because they're opposite to each other, right? So now, from there, let's see, can we understand polarization with this? So here, we have EXZT over here, right? And we're doing who is delta equal to 0 for now, all right? We're doing delta equal to 0 for now, so we have this over here, right? At this point, we have also inclination angle here, AY over AX. So look at this one here. This is the magnitude, right? This magnitude, this magnitude over here at z equal to 0, if I have g equal to 0 and also t equal to 0, so I put g equal to 0, t equal to 0, that's magnitude here, that's correct magnitude, then this becomes 1, right? T equal to 0, g equal to 0 becomes 0, cosine 0 is 1, so I have only this part, right? That's the magnitude, right? That's the magnitude, highest magnitude. Then if I have now g equal to 0 here, so z equal to 0, this means I'm looking at a plane right here. This is a plane over here, z equal to 0. So that's my xy plane. I'm looking at from that plane how it's propagating, right? So at different point of the value. If I go from g equal to 0, t equal to 0, I have this one here, the highest one. So look at here, omega t equal to 0, right? And also this plane always g equal to 0. So I have this tip over here. So this is the right here. This is the tip right here. So this tip represent this tip over here. Is t equal to 0, z equal to 0, that omega t equal to 0, that's right here, right? Now your wave going down this way, right? Propagating this way, right? So at this point here is omega t equal to pi by 2. Say at omega t equal to pi by 2, I'm still looking from my xy plane. Then omega t equal to pi by 2, right? Z equal to 0. Then your magnitude becomes 0 right here, right? So this point over here represent this point. So it was here and coming down, right? This way. Now it's going down here, right? Your magnitude is still increasing now again. So at this omega t equal to pi, pi over here, this is omega equal t equal to pi, omega t equal to pi, right? And that is increasing again here to this point, right? So then after that is again decreasing. Can you see that? Right? So that means your magnitude following this line back and forth all the time as your wave going forward from a reference point t equal to 0 and z equal to 0, and you watching. So your this plane is right here. This plane, if you move it forward, this plane is right here, right? Z equal to 0, t equal to 0. And if you're watching the wave propagates with respect to time, when you're holding the plane at z equal to 0, you will see that your magnitude of the locus top of the vector is going back and forth with this line, right? So this is called linear polarization, because your tip of the vector or locus of the vector propagating through the media is following a linear line. So that is that. And when a y equal to 0, your inclination angular psi equal to 0, and also when your let's say ax equal to 0, then it could be 90 or negative 90. That's the inclination angle, which is the angle of your locus vector making with respect to the reference angle here. This is the right angle here. All right. So that is your angle. Angle can go from 0 to 180. And or negative 90 to positive 90. All right. So that's the linear polarization when your tip of the traveling vector magnitude follows a linear pattern. Okay. So now what is circular polarization? I think we should get to the in next video, because it's getting longer. Okay.